Good morning, everyone. Now that we've talked a lot about derivatives and started to get a hint of how we can use that to find things like maximums and minimums, we're going to start going into more detail about how we can use derivatives to describe a curve. Okay? So our first definition is related to that idea of finding a max or a min. So a critical number is some number c such that the derivative is equal to 0. And the point on the original graph, okay, the point C f of c is a critical point. Okay, so again, visually, right, on my function, maybe it's something like this. Okay, up there at the vertex, okay, that's going to be a critical point. Okay, on my derivative, okay, my derivative would have to be 0 at that point, right, because the slope of the tangent is 0 there. So let's do a quick example of how to find those. Okay, so determine the critical points of this cubic function here. So in order to do that, I'm going to take the derivative. So f prime of x is equal to 3x squared minus 8x plus 2. Now, critical numbers make this equal to 0, so I'm going to set that equal to 0. Okay, now my next step here would be to factor this, okay, and try to get roots. So let's see, two numbers that multiply to 6, add to -8, that's not going to happen. Okay, so in this case, it's a quadratic, so I could go to the quadratic formula. And if we do that, we're going to get x is equal to 4 plus or minus the square root of 10 all over 3. Okay, so you get about 2.387 and 0.279. Okay, those are my critical numbers. Those are the values that make my derivative 0. Okay, so to find the actual points, right, I would go back to my original function and determine what is f of 2.387. And that equals negative 12.417. Okay, so my critical point is at 2.387 and negative 12.417. Okay, and similarly, okay, I could do the other point and get something kind of like that. Right? My other point ends up being 0.279. And when I plug that into my function, I get negative 7.732. Okay, so we've been doing this for a little bit now, right? If I want to find some kind of a max or min, take the derivative, find its roots. That's the point. Okay. Now, in terms of what it identifies, pardon me, okay, there's kind of 3 situations where this can actually occur, right? So now that I found the points, the question might be, is this actually a maximum, or is this a minimum, or is it maybe neither? Okay, right? Because it could be, like in this first case, a maximum, okay, and it could be like this and a minimum. The slopes are 0 in both spots. But it's also possible that we just get a part where it gets flat, and it's not a max or a min. Okay? So how am I going to decide that? Right? Once I know where my critical points are, how do I figure out if they're a max or min, or maybe they're neither? Okay. So one way we can do that is if I had some way of figuring out where the function is increasing or decreasing, right? So for instance, with my first one over here, on this side of the function, my function is increasing, and on this side is decreasing. So if I knew that, okay, then I could say that's going to be a maximum because it was going up and now it's coming down. Okay, similarly over here, it's going to come down and it's going to go back up. It was decreasing and increasing. Okay, so if you worked your way through the activity yesterday, hopefully what you noticed is in the derivative, right, if a function is increasing, but when this is going up, my derivative is positive because my tangent lines are all positive here. Okay, and when my function is decreasing, when it's going down, my tangent lines are negative. That's what this next part is going to describe here briefly. So this is kind of a summary of that first investigation from yesterday's notes. Okay, if I have some interval a, b of a function, if my derivative is positive, so greater than 0 on that interval, then my function has to be increasing on that interval. If my function is negative on that interval, then the function is decreasing on that interval. Combined with the critical points gives us what's called the first derivative test. Okay, so if I know what my critical number is, I have C. Okay, if my derivative switches from positive to negative at C, right, it switches from increasing to decreasing, then I must have a local maximum there. If my derivative switches from negative to positive, right, it was decreasing then increasing, then that means I have a minimum. Okay. If it doesn't switch, then I realistically probably have the third case that we mentioned. It just flattens out, but it keeps going. Okay, so let's do an example of how that will work. So example 2, find and classify the critical numbers of f of x equals x cubed minus 12x. So again, we'll start with our derivative. F prime of x equal to 3x squared minus 12. Okay, I want to find the roots of this thing to find my critical numbers. 0 equals 3x squared minus 12. Okay, there's a couple ways you can solve from here, but let's keep with factoring for a moment. So I can common factor out of 3. Okay, and so we get 0 equals 3, x minus 2, x plus 2. So that means my critical numbers occur at 2 and negative 2. Okay. Now, the key thing here was when my derivative is positive, it's increasing, and when it's negative, it's decreasing. So I want to know what's happening right around 2 and negative 2. Does it switch? Does it not switch? So re-asking that, I really want to identify where my derivative is positive. Right? Where is it positive? And where is my derivative negative? Okay. And you did this in advanced functions. Okay, so I'm going to draw a little interval chart. Okay, and we'll check out what's going on. So my two roots are 2 and negative 2. So my first interval is from negative infinity to negative 2. Okay, my second interval is going to be from negative 2 to 2. And my third interval is from 2 to infinity. Okay, then down the side, I'm going to list my different pieces of my function. So I had a constant 3, a factor x minus 2, and a factor x plus 2. Constant 3 is always positive. Okay, x minus 2 in my first interval when I'm negative 2 to infinity. So again, one way you can check is to do a little test, right? So maybe I try, in my head, I'm going to try negative 4 because it's in that interval. Okay. Negative 4 minus 2 is negative 6, so this is negative. Okay. In my middle interval, I'll try 0. So 0 minus 2 is negative 2, it's negative. And my final interval, this is positive. Okay, for x plus 2, a plus. Sorry, I don't have positive there, I have negative. And this is negative, this one is positive, and this one is positive. Okay, so this was my derivative. Okay, so overall, my derivative was positive here, negative here, and positive here. So what does that say about my original function? Well, my derivative was positive, so my original function was increasing on this interval. Okay. In the middle interval, it was negative, so my function was decreasing on that interval. In the final one, it was increasing. So what happens at negative 2? Right? At negative 2, it switches from increasing to decreasing. So negative 2 is a local max. Okay, it peaks there. It went from increasing to decreasing. Okay, at the other location, at 2, it's the other way. It switches from going down to coming back up. So 2 is a local minimum. Okay, and that's how that works. So again, you can use the derivative to find where it's positive and negative, which will help you decide where it's a local max or a local min. Okay. The other thing we can talk about here is a bit about the curvature, because in some ways, there's kind of two ways you can be increasing and decreasing. Okay. This is the idea of concavity. Okay. So the basics of this is a brief example. If my function looks like this is called concave. This is concave up. Okay. I can have situations where it switches. Right? If I have, say, a basic cubic function like that, okay, over here it's concave down, but on this side it is concave up. Okay, so it has to do with the direction of the curvature. I think the way that the activity described it, again, if you're in that through, was on my concave down, if I was drawing my tangent lines, they'd all be above the curve. If we're concave up, they're all below the curve. So if we go back to talking about our position functions, okay, this is something we talked about before. Okay, it's going to be a little hard to describe on the screen here. But if I look at, say, my concave down, so maybe I'll draw it again on the side here, right? We talked about this idea of acceleration and deceleration. So here I would start with a steep positive slope. Okay, it's getting less steep, less steep, less steep. Okay, so I would say that is decelerating as I go around. Okay, it's slowing down. Now, acceleration has to do with the second derivative. So because I'm slowing down, my acceleration is negative. And that comes from the second derivative. Okay, similarly for concave up, okay, if my curve is going the other way, right, my function started as large negatives, okay, and then they slowly get more and more positive. So this is accelerating. Okay, so my second derivative would have to be positive. So to decide if I'm concave up or concave down, we're going to use the second derivative. Okay, so here's how this test works. If you can take two derivatives, right, it's twice differentiable, and the derivative exists. Okay, on an interval, that's the setup, but I have some function where I can do two derivatives. This is the test. Okay, if f double prime of x is greater than 0, right? So if my second derivative is positive, then the function is concave up. Okay. If my second derivative is negative, less than 0, okay, then it is concave down. Okay, and last but not least, if it's an inflection point, right? And actually, I don't think I wrote that down anywhere. Inflection point is where it switches, okay, or has no concavity briefly, I guess. Then the second derivative is going to be equal to 0. Okay. Now, just like for max min, okay, the statement doesn't really work the other way quite, right? If I know the second derivative is 0, okay, it could be an inflection point, but I have to check. Okay, just like for the first derivative, when I have a critical point, it could be a max or min, but it doesn't have to be. I have to check. Okay, so for example 3, we'll go back to we were both talking about and test for the concavity. So we had that up to a moment ago, but as a refresher, right, my function was x cubed minus 12x. My first derivative is 3x squared minus 12. So that means my second derivative is 6x. I want to determine where this is positive or negative. So we're still thinking about roots. Okay, so 0 equals 6x. So x is equal to 0 is the only root that we have. So I'm going to do another little interval chart here. Okay, so I have from negative infinity to 0, and from 0 to infinity. Okay. And the only factor I really have is the 6x, so I'm not even going to separate it. It's just 6x. Okay, when I'm less than 0, this is negative. When I'm greater than 0, this is positive. So my second derivative, okay, is negative and positive. And my overall function, okay, so this is concave down, and this is concave up. Okay, and just to emphasize that, as a little sketch here, right, that original cubic function, okay, it looks something like this. Okay, and that's exactly what's happening, right? Up until 0, in this region here, it's concave down, and it flips around, and it's concave up on that side, and that's what it's doing in that interval. Okay, we're almost there. Okay, so we can use that concavity to actually help us identify max and mins as well. And in some ways, this is a little bit faster than doing the first derivative test because I don't have to do that interval chart and work out all that different stuff. So here's how it works. Okay, if I have a critical point, so f prime of c is equal to 0, and I check the second derivative, okay, and I find that the second derivative is positive there, then that means f of c is a local minimum. Okay, and I know this messes with people's minds because I said it's positive, but it's saying it's a minimum. You don't remember what that means, okay? If the second derivative is positive, that means I am concave up in that region. Okay, so my critical point is at the bottom of this, and it's going to be a minimum. Okay, concave up gives me a minimum. Okay, similarly, if f prime is 0 and f double prime is 0, sorry, is less than 0, then it's local max. Right? When I say that f prime is less than 0, that means it's concave down. So if I have a critical point in here at the top, okay, it's going to be a maximum. Okay, if they're both 0, then this test didn't work. Okay, something's going on and I can't use it to figure it out. So we probably just go back to the first derivative test. So again, second derivative test is probably faster in some ways, but it doesn't always work. Okay, so let's test that out. Okay, we're going to verify the results of example 2 using the second derivative test. Okay, so from example 2, right, our critical numbers were -2 and 2. Okay, so okay, I start with -2. Okay, what is f double prime of -2? Well, that was sorry, it was -6. It was 6 times -2. That's -12. Okay, so my test says my second derivative is negative. This means, so therefore, local max, right? This means I'm concave down in that region, so it's max. And that's what we discovered before. Okay, similarly, if I do f double prime of 2, okay, that's 6 times 2, which is +12. So therefore, a local minimum. Okay, it's positive, which means it's concave up, and I have to have a minimum. So there's the 3 tests, the 4 tests, and then just using the to look at that. So the practice for today is just basically using those skills over and over again. Okay, so it's from 2 different pages. Okay, but there's about 8 questions there to practice those skills. Make sure you understand the tests. Okay, next 2 days we'll be applying them and using them to do curve sketching by hand. All right. Thank you very much for watching, and I will see you tomorrow.